Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we have a great session now. The previous session was really interesting to hear what the research community was doing. This session is flipping it the other way, really, and talking a bit about what we're doing here in Microsoft and Microsoft Research, and on both the sort of infrastructure side and also on some of the research side here as well. So great pleasure to be introducing David here, who works for an organization called Global Foundation Services that runs Microsoft's sort of infrastructure across the world. And I think this is, you know, I've seen his slides. It's a great insight into what powers Microsoft, really. So over
Great.
to David.
Thanks, Kenji. So thanks for having me. Thanks for the interest in the topic today. My name is Dave Gauthier. I run our data center architecture group in Global Foundation Services. Really responsible for the technical strategy and the availability profile of the physical data centers we build around the world. I'm probably the only person in this room who doesn't have some sort of degree in computer science, so go easy on me. But I've been in the company about 15 years, and what we find a lot in the data center physical industry is that people just kind of fall into this space. My background is in a little bit of computer science, a little bit of broadcasting and communications, and just a love of wires and plugging things in, and so I kind of fell into this space. But yeah, I really want to talk about the growth of the cloud and how that's fueled our investments in data centers around the planet, and kind of how we tackle that. So Microsoft, as a lot of people know, runs a lot of different cloud services. We've actually got, you know, probably the 5 big ones that everybody talks about or knows about: Office 365, Windows Azure, Hotmail Windows Services, and the things that power the back end of Windows 8, Bing, and the Xbox Live components. But there's about 200 different services that make all this up. We're delivering to over 1 billion customers around the world, 20 million businesses, and hitting a ton of markets in a ton of different languages around the globe. The main point of this, there's some really big numbers here, billions and trillions, but it's really more about the scale and the need that we've had to scale over the last probably 4 or 5 years since things really started ramping up. And to take something like Office 365, which is the fastest growing product in Microsoft history, we're moving all these folks on Exchange and SharePoint into the cloud as a service. We need to be building data centers in new markets all the time. We need to be innovating in our data center space. And then for Windows Azure, where there's robust competition for IaaS and PaaS services in the cloud, we need to be able to do that at very, very competitive rates and be able to do it very, very quickly and agilely. And so building new data centers, innovating in their efficiency and in their cost to deliver is key to doing that. Around the world, these are kind of the big data centers we talk about. I think we have a number of presences here in North America. We're also turning up new services in Asia and China around Office 365 and Azure, lighting up Australia and Brazil as well. A lot of people ask what goes into the selection. How do we decide where to place data centers? And really, it's about 35 things. We used to like to call it 31 flavors, and then it grew. But it's about proximity to customers. It's about the usage and the utilization and the speed and latency that these services are consumed under. You know, a lot of cases we have customers come to us and say, "Hey, why isn't there a data center in my town?" And it's like, well, I could build a data center right next door to your office building, but in reality, both of these are going to transit all the way back to Amsterdam before they come back here. And so having real proximity to the customers from a network standpoint is super key. Having robust scale-out energy and fiber infrastructure is another really important element. These data centers are getting into the tens of megawatts of capacity. We're going into a lot of rural locations that have lots of land that we can expand, that we can keep growing and growing and growing without having to start on a new site. And so having an energy grid that we can support that from is really key, and having growth in fiber is key. And the last piece is around the skilled workforce. You know, people who can build these data centers. We're turning up, you know, hundreds of millions of dollars of projects in a very short amount of time. So we need to build them, and then we need to operate and run them and take care of the servers and the electrical and mechanical equipment inside the data centers. We've been on a bit of a journey and I've been involved with this kind of, I don't want to call it day one. We built our first data center at Microsoft in 1986. It's about half a mile that way. It still exists. It's called Building 11. And that was really about corporate IT functions. But we built our first internet-facing data center in 96. That's north a little bit in Bahl. And when we really started going into the internet space after 96, 97, 98, 99, through about 2001, 2002, we were really going out and buying co-location, third-party leasing space and growing into that. And I think the main reason I talk about this is because those stuff was just about rent. It was just about a place to put your servers and put your devices and run them. A lot of companies still run this way today. And there was never much thought of efficiency or energy efficiency or resource efficiency in those types of data centers because they were fully landlord-tenant relationships. Who cares what the tenant pays? I'm just going to build this thing. And so we have this metric we call PUE. It's an overly simplistic metric, but it's one that people can grok easily. That's about efficiency. And so it's about the amount of energy coming into the building versus the amount of energy being consumed at a compute resource or device or network device. And so it's a simple overhead metric. And it's a good way to talk about things. In 2007, we had eaten up all of the extra lease space that the dot-com boom had afforded us, and we realized we needed to start building data centers ourselves. It's the first time we really focused on designing for efficiency, designing for operation, and how we actually deploy in the environment and get a little bit more speed into what we were doing. And we were able to knock a number of points off of the PUE metric straight away just by focusing on it as an owner rather than as a tenant. In generation 3, started landing in 2009, we played with containers. And I think a lot of people probably have heard about containerized data centers. And we really went all in on this. We built a very large facility in Chicago where we were deploying 40-foot shipping containers filled with servers. We get about 2,000 machines into each box. We could roll it in off of a truck, and within about 8 hours, we'd have our bits imaged on top of that, and we'd be serving traffic off of that cluster. Highly efficient from a workflow and a scale standpoint, and also highly efficient from an energy and a water consumption standpoint. So it was just a super big win-win. The other element that we brought in to that container farm is the first time we looked at what we call differentiated SLAs. So the typical data center environment today, if you were to go and hire somebody to build you a data center, they're going to build it to 5 nines availability. Really quick, very high mean time between failure, very low mean time to recover, and it's always running. You can treat it as a permanent resource. Now we know as software developers and as service developers that there are a whole bunch of other things that can go wrong besides just the power going out on the infrastructure. And so if we want to design our applications better, we're going to design them for all the faults that can happen in the system. And so we took advantage of that just 5 years ago and actually provided a 3 nines environment for our server infrastructure and recognizing that it can fail. And they have failed. In one instance, we took a double lightning strike on 2 separate substations that connect this data center, and those servers didn't have any generators behind them. And so we dropped tens of thousands of machines. Great thing is, we've got some smart people here. Nobody outside of Microsoft noticed. The applications kept running, the users were available, everything went exactly as it was supposed to happen. It was a lot of operational work on the other side to recover the environment, but we got there and we learned from it.
So you do have 5 nines.
You have 5 nines at the service, right? 5 nines at the service, 3 nines or less at the infrastructure. We took this a little bit further in our Generation 4 facilities, and these are what we're still turning over a number of these facilities today. And we moved more of those modular components into containers, and we also took advantage of outside air to cool them, so they were even more efficient, and they used a heck of a lot less water. About 1% of the water of this my laser pointer's not on there. This data center versus this data center, huge reduction in the amount of the water that was consumed. And that's really about fast time to market and sizing across to our demand. Now, what am I working on today? Working on our Gen 5 infrastructure, and we're just announced investments in Cheyenne, Wyoming, and Des Moines, Iowa, West Des Moines, Iowa, of nearly $500 million for new data center construction. This is our Gen 5 builds that are kicking off. This is about integration. This is taking that understanding of the service and the application another layer deep into the infrastructure, where we're designing the data center, the server, the network, the workflow and operational tooling all together with Windows Azure and with the team behind Bing Autopilot, which I think we've talked about a fair amount in the past. It's really about resilient software. So the software can deal with any kind of failure within the environment. It's on common infrastructure. We have much fewer server products or SKUs than we've had in the past. And it's really about being flexible and scalable so we can get all the benefits we had here with an integrated system. We're able to kind of rev the code of the data center, kind of compile the availability to be what the service needs to run. One of the things that goes into that, and this is an eScience workshop, so I figured I'd try to at least show you some of the math we put behind this stuff. We're running over 1 million servers. So that means we have a really nice, big sample pool to pull from for how infrastructure runs. And one of the most notable and simple things that we did with this is we modeled out our data center topologies and the temperatures outside and the temperatures inside and what the weather was doing against the device failures on the systems. And the number one thing that fails in big infrastructure is hard drives. The number two thing is systems that support hard drives. And I don't remember what number 3 is, but it's way down the list after those two. And so we were able to find that depending on the inlet temperature that the device was seeing, we could look at our annualized failure rates and really understand how hot we could run the data center. And so we took this information, we've ported it into the designs. We're running our data centers 10 to 32 degrees C with a time-weighted average of 24 degrees C to get the best energy efficiency possible out of this. And this has actually driven our PUE numbers down on that last slide from the 1.2 to the 1.07 range, mostly in hard drive temperature knowledge. We've also done a lot of other things. Removed all the unnecessary components. No spinning. No CD-ROMs, no USB ports, things like that. But we're also running at a European voltage now. We're running 1 voltage across our portfolio, 415 volts. It's the most efficient. We're able to take extra transformations out of the design, and we're able to have commonality in our supply chain worldwide as a result. Let's see. The other piece is around, from these high temperatures, how we get that major savings is by using outside air cooling. We use what's called adiabatic cooling or direct evaporative. Like if you're sitting on the beach and you've got a spray bottle and you spritz yourself, that's how we cool our servers. We open the windows and we spray a little bit of moisture into the air to bring the temperature down on the super hot days by introducing humidity. So it's super, super efficient. We've got these running almost around the world. There's only a few locations where we can't do this. Most of that's in Southeast Asia where it's very humid at the same time that it's very hot. The other interesting pieces that we're working on are the next elements. We've got a team working on research around distributed generation and also fuel cells. Now we've got a team at MSR and GFS and along with the UC Irvine National Fuel Cell Research Center working on directly powering servers off of natural gas. And so we have a rack of servers where we're converting natural gas via I'm going to get caught on this one, I think it's a PEM fuel cell, to actually deliver direct DC voltage into the servers. And this has been really, really successful. It's really exciting because if you know, the grid is horribly inefficient at delivering energy. Something like 40 to 60% of the input energy is actually lost in the distribution before it comes into a data center. And so if we can take natural gas straight into the data center, we're able to run a tremendously higher efficient data center infrastructure overall. And so this is one of my favorite things that we're working on. Other piece, we're actually taking that a step further. And in Cheyenne, we're working with the local university on a wastewater treatment plant where we're recovering methane gas coming off of this treatment plant, and we're then running that into a fuel cell to run servers. And so we could see ourselves, all jokes aside, kind of powering these things off poop, which is pretty exciting. Let's see. The other nice thing about this is that there's a lot fewer parts. A lot fewer things break. And so the reliability of the system increases. Fewer moving parts, fewer broken pieces. And we're able to have a common system, again, worldwide, where all we need is a natural gas feed, and we're ready to go. And so, just to summarize, I'm a couple minutes over, but The other element that we're really working at Microsoft is shifting the thinking. I think there's been a lot of talk about One Microsoft and about doing things at cloud scale and really thinking about new ways of developing apps, new ways of delivering services. And so these are kind of key themes that when I talk to developers here, I'm really nailing on a daily basis. You need to think about resilient services. How is your app going to deal with not only a power failure or a cooling failure, but also somebody fat fingering the code into the router? How are you going to recover from that? So these brittle services and brittle networks need to start getting stronger. Solve hardware problems in software. Software company, we don't need to throw a bunch of redundancy or extra components at the problem. Let's figure out how to solve that. Self-healing. And last piece is probably the more critical element in scaling. How are we enabling the business? We need to be able to go out and come up with new products. The data center and the servers and the network are not the product that Microsoft sells. The key thing that we're looking at doing here is making sure that that infrastructure is there to enable developers, enable researchers to be able to spin up new ideas, test new hypotheses, and get them out to market faster or solve that problem. So that's about it. There's some slides, there's some content here on the back end that people are welcome to go out and check out. We've got a robust blog at Microsoft.com/data centers and a whole bunch of other great information on Azure and O365. Are there any questions, please? I should have said, ask me questions as I go. I forgot that part.
Number one, things that fails in the data center are hard drives. I just want to know how the is using SSD drives to change that in the system. Well, of course, there's additional cost, but when it comes to breakdown,
yeah, absolutely. So the question was, how does hard drives being the number one failure change if you start moving to SSDs, recognizing there's a cost premium there? We find that the SSDs have their own issues, but they're more reliable to temperature variation, absolutely. But I think that we find that we use them for different things. And so if we're going to go out and build hundreds of petabytes of storage for Azure storage or for Bing or something like that, the economics of SSD just break. But they are a little bit more reliable for temperature variation. And there's some interesting work going on in understanding exactly how SSDs respond to temperature and what that looks like from a drive life perspective as well as a read-write perspective on the type of flash we can use.
So over time, things will break.
Absolutely.
And do you actually try to go into these containers and repair things, or do you just at some point recycle?
Do it, yeah. So do we fail in place in the containers and forget about it? Do you have another question? Or
No, that was
it. So no, we don't. Unfortunately, computers haven't gotten cheap enough yet. There is the way that we treat the containers and actually the whole environment for that matter is about a carefully crafted percent of the infrastructure that can be down at any given time and for how long it's down. And then we kind of target that for when we're going to go in and repair it. But for right now, most of the computer sled is just a little bit too expensive to forget about it unless it's right towards the end of its depreciation cycle. Okay, another? Go.
You mentioned about utilizing the literally generated to data centers, but what about utilizing the heat? I didn't know, I remember in some newspapers and some magazines I saw that they are utilizing heat generated from some facilities to greenhouses and gas. Do you have any plans for that?
I can't speak to any plans that we have on that on the drawing boards, but it's absolutely a huge opportunity, and we are looking at it in certain locations. Waste heat recovery for data center is a great opportunity. The challenges are it's not quite high enough grade waste heat. Like if it was like 300 or 400 degrees, it's more portable. You could take it somewhere. But when it's only 120, 130 degrees, it's hard to transfer that into water and actually move that water a distance to actually get a huge amount of benefit from it without putting the greenhouse right next door. I'm not going to say that that's out of the question, though.
The question I had was about Amazon Glacier.
Yeah.
Is a long-term archiving service.
Sure.
which is very cost effective. Do we have any thoughts on that?
I'm sure that someone in the Azure space is considering long-term storage. There's a number of different technologies that we could choose from to do there, so I can't speak to it definitively.
Sure.
Do you think it will be possible at some point to see at the virtual machine level the energy consumption of the machine, provide an API for that?
An API to pull the energy consumption for machine? Absolutely. And actually, this is kind of one of the challenges of the overall OEM ecosystem is that in 1999, I was buying servers from Dell and HP that had that telemetry coming off the hard drive and the power, or off the motherboard and the power supply already. And then somewhere along the line, they wanted things to get cheaper and cheaper, and that was like one of the first things to go. And you're starting to see those features come back in natively in the power supply and the chassis managers and some of the new products. So those are there in the higher end products especially.
Okay, I think we'll move on now. So thanks, David.
Okay, thank you.
So delighted to introduce Victor Bahl, who runs Mobility and Networking Group here. I think what's really exciting is, we're obviously talking about cloud, but obviously mobile devices and services. So Victor actually helps to really define the strategy of the company on networking. So really looking forward to Victor's talk. So thank you, Victor.
Thank you. Thanks. Hi.
All right. Thank you for giving me this forum to say a few words. There's a lot to say, but I'll try to condense it very quickly. So, and we have, Microsoft has, and Google and Amazon and everybody spending billions of dollars on cloud. You just heard that talk. And it's been going on for many, many years. And so all these companies, including ourselves, have been optimizing the heck out of the cloud infrastructure itself. And now that we have both the devices and a services company, we're building both the devices and the cloud. But there is still an open element here that I want to talk to you a little bit about. But let's start with some ground truths here. So we know that in order to build great services, we need to have the ability to get to those services really quickly and really optimally and fast. And the latency and the jitter that you experience is actually directly will contribute to how you use those services or how you think about it. So while we're optimizing all the cloud, and it is important to sort of think about how you connect to it. All right, and these things matter. They matter a lot. I just picked up quotes. We have obviously our internal measurements as well, but I picked up some quotes of people that you might recognize claiming publicly how much it mattered to their revenue in terms of looking at something simple as latency, right? So if you increase the latency to your services, you're actually going to lose revenue. If you make it better, people are going to come towards you. So we see this again and again, both internally and externally as well. So I think the more famous quote is from Marisa Myers, which I've listed as first. So now, if you think about latency as that component that you want to reduce, then let's simplify this problem. I mean, there's latency in every part of the system. So there's something going on in the client when the request is sent. Then you send the request over the network to the data center. It munges on your data. It sends it back. The client processes it, post-processes, and presents it to you. So there are really these three components. Now, in the past, we have focused very heavily on the data center, right? In fact, Albert's going to talk next, and he'll tell you about some of the innovations that he himself has been involved with, which include removing the network from being bottlenecked to the server. So the servers can now work on line rate and pump data out in line rates and can be fully utilized. Similarly, software load balancers, and most recently, we've been sort of working on trying to optimize the bandwidth utilization between data centers. So we've done that, but like I said, there is a gap, and the gap has to do with the internet. So no matter how optimum you are in one space, you're not going to really be able to do great thing unless you sort of think about the internet as well. So this is a talk about that. Now this is a little experiment I did a while ago from my own office. This is using one of our phones, and it was just a ping, a trace route to one of the Google sites. And you could start to see that depending on the network I use, in case of Wi-Fi and cellular, the number of hops go up. And with the number of hops, the latency to it goes up. So now if you say I want an SLA, I want to build a service which performs like this because I want all the computes to hit me. You know, if the packets don't even get to your cloud, you're going to have problems. And we repeat this experiment again and again, and you know, we see the same things. Now, why is this so? Because the internet is actually very, very complex, right? This is a gross simplification of the internet. And what is it? It's a bunch of ISPs, right? They talk to one another. They have this nice or bad protocol, BGP. And based on policies, your packets get routed. And at any given point, it's not really clear what route it'll take. So if you don't have any clarity on what route it'll take, you don't have clarity on how many hops it'll take, and then you don't have clarity on how fast or slow it'll get. And there are lots and lots of networks, right? This is just some data to sort of show what those networks are. Now, if you add to that the mobile world, right, which is the huge deal now, you have great complexity in the mobile world as well. In fact, a lot more complex than the IP world, right? So the IP is represented with this little internet here, and a lot of the other stuff is just mobile. And then there's measurements, and you've seen papers, so you can see papers which tell you that latency just goes up. This is on a 3G network. You can see T-Mobile with 450 milliseconds. This is not singling out any particular ISP here, but just general measurements. And then when people say, well, LT is coming, LT is a lot better, but there too we see the jitter, and we see at least 70 milliseconds average latencies to our data centers. Now, if you don't believe me, you can actually download this little app that is available on Windows and phones and everything else, and you can try it for yourself. And you will see, because it will measure the latency, and you will see all these numbers are actually absolutely correct. In fact, you can start to see how good your ISPs are and what you're getting. So now, what is the question? The point is that when the packet leaves the device, you want it right away. You don't want anything, any time spent on the network is wasted time, right? So what do? You say, well, we're going to build all these massive data centers all over the world, which is what we're doing. And not just us, everybody's doing that. You saw a much nicer picture of this. I just sort of put it up just a minute ago, or just a speaker before. But really, we're building all these big data centers all over the world so that you can get to these places from wherever you are very quickly, right? But is this really a solution that's enough? And the assertion is that it's not, because the cost for building these data centers is very large. The cost of both building them and operating them and keep the equipment going and everything else is very, very large. So what's another alternative? Another alternative is build lots of these ones, but build small of these data centers, right? So for example, we have a team called Bing Edge, which kind of does that. And then the idea is that you spread thousands of these on the internet, and then wherever you are on the network in the world, you get to those guys fast, right? And then once you get to those, you can at that point decide what do you want to do with the packet. Do you want to compute there, or you want to send it back through some really good, better networking from there to your mega data centers. And so then systematically you break up this really complex problem into its pieces and start to approach each of these pieces individually. Okay, so then like I said, you tunnel from these micro data centers or cloudlets, they call it in the literature. So these cloudlets, what are these? They're capable of doing a whole lot. So right now in today's world, they are really an SSL termination thing. And they're a proxy for MS services or any other services that Microsoft runs. So for example, you'll say hit the cloud, and it'll terminate the TCP connection there, and then you have a persistent TCP connection from there, from the edge to the cloud. And so that way, if there are losses in the TCP, those losses get mitigated. Not the losses don't get mitigated, but the delay that happens because of those losses get mitigated. But then you can also do a lot of edge computing stuff. This is sort of new things. You can actually use these micro DCs to do resilient routing. So now, if one path is not going well, you can imagine creating an overlay network on top of that and start to send packets around that network. You can keep doing service and internet monitoring. You can proactively see if something is going bad or good, and so you can react to that. And then you can do a lot of things for mobile computing, and I'll give you an example of that. So here's one benefit that which I think is fairly significant and you will appreciate. So I don't know how many of you know, but when iPhone first came out several years ago, there were lots of these news articles which said that it brought down the networks in New York. Does anybody remember any of this stuff at all? You remember it? So you guys, okay, so bad, I guess things don't last long. But nevertheless, there was this big thing, which is that the networks were just brought down. And the question was, what was going on there? Why did the networks go down? Well, the way the networks went down is because everybody, iPhone and all smartphones, are trying to save battery, right? That's sort of the most, and so all our traffic is very bursty. So when you go to the website, you send a bunch of packets comes, and you're done. Then you watch the page and whatever. So really, what the iPhone guys were doing at the time was they would put the radio on low power mode. Then when the data was there to transmit or receive, they'd put it in high power mode, transmit the data, and as soon as it was done, bring it down to low power mode. Makes sense. But really, that didn't really work well with the telcos, because what was happening was that the whole telco business is based on circuit switch networking. They come from that piece of world. So every time you set up a connection, a whole set of resources are set up from your device right onto entire network to the point where they go to the internet. And so every time you bring the radio down, a signal is sent, bring down the resources. So now, as you're going back and forth, as you're sending data back and forth, these signals are going back and forth, right? And as the signals are going back and forth, the network gets overloaded and can't deal with it. All right, so they figured this out and then said, okay, you can't do that anymore. So what you have to do now is you have to, when you're done with the data, you can bring it down to lower power, so 1.6 watts to 1 watt, but you can't really bring it down for an additional n seconds, okay? And so if you don't bring it down, then you can fix any perturbation and you can sort of solve this problem a little bit and the energy is not lost. Well, so that's the data here. So LTE consumes about 1.5 watts. But the chip is active for approximately 10 seconds at 1 watt doing nothing. All right? Now, imagine if you have this cloudlet, and a cloudlet is a proxy for your phone. So now the cloudlet holds on to your connection, but you tell the cloudlet, I'm done. You bring your radio down, the cloudlet holds on to the connection, which is in the wide side, and you can, things are okay. So now if you do just a little bit of calculation, you find that 1.6 watts, that's here, times whatever speed up, because now you're sending to cloudlet, you're not sending it to or MDC, you're not sending it to the big cloud. So that's the speed up, times 1 watt times 9 seconds. That's the amount of time you save because now your radio is down, but you can still send the packets. That gives you a saving of 10.6 joules. This is amazingly significant saving. Because if you have 20 network transfers in, let's say, 1 hour, or and there may be email notifications, etc., then you can save up to 26% of your battery. Okay? Now, no matter what, I mean, if you're in the field, you already know that energy management is amazingly hard. This kind of saving is just incredible, right? And if you sort of let that whole thing keep going, and with the argument, if you sort of increase the number of transactions per hour, you start to see how much saving you can get from this little thing. All right, so because you now have a cloudlet in the edge. Now let me show you, so this is pretty good. Let me show you one more application and then I'll be done. So in this particular application, we talked about new services and I talked about edge computing and things like that. So let's take something like object recognition. You all heard about augmented reality, you probably work on that, and object recognition and things like that. So for all of these sort of applications, the building blocks are similar. Let's say you take face recognition in this case. You detect the face, you align it, correct? You then extract the features from the face, and then you match those features to some database, which will tell you what the face is, right? Now, if you do a lot of this detection, for example, just on the client, you take a lot of time here. But if you send it to the cloud, or this cloudlet that I'm talking about, then you're serving less time. But what is interesting is this graph, okay? So what this graph is showing is on the horizontal axis is the time spent on computation. On the vertical axis is accuracy. N is the number of features that have been extracted. So now depending on how much computation time you have, that many features you can extract, and that'll give you the amount of accuracy you get. And this is true for pretty much everything that we do with imaging or vision or even speech and even search. The graphs look very similar, really. The more computation time you have, the better number of features you can extract, the more accuracy you can get, okay? Now, which means that every millisecond that you're using on the network is wasted, completely wasted. So all of us, all our companies, Microsoft in particular, is very, very deeply trying to sort of fix that problem, okay? Let me show you what it means viscerally. So here's a little thing that my intern actually put together. And what you see is, just to set it up, you see the video of her holding a device, and she's taking a video of people moving. And they're just moving at regular speeds. And the system is using the best face recognition algorithms that we have, the state-of-art face recognition algorithms, to see if she can detect faces. And this is going to be very fast, so you will see how it goes. Hopefully you'll catch it. So there are 7 faces in here. Okay? You will see there's 7 people walking by, right? And we are taking the video and doing face recognition on them. So now when you're able to send this data to a computing device 5 milliseconds away, the system is actually able to recognize all the 7 faces. Now let's say you put it 75 to 85 milliseconds away, the system is going to try to do the same thing, but now it recognizes only 4 of the 7 faces. Okay? So, because it just can't keep up, and the time that is spent in the latency is lost. So now, whichever company, whichever one of us actually licks this problem, obviously you will go towards that company, because now we can, even if we have the best minds working on this, we really solve the problem because we fixed the latency issue. All right? So there's a whole lot of stuff you can do on the edge. This is a laundry list of things you can do. A lot of these are open problems, by the way. It's not necessarily, none of these things are solved, but we are working actively on it. I talked about caching, and caching is, if you have the data, you just send it. SSL termination, you can save a lot of bandwidth too, because you can do proxying, and there are ideas here. Not have time to go through all this stuff, but there's a lot of stuff you can do at the edge. Now, where do you put these clients? Here's just a couple of small ideas. In the wireless space, the way things work are you've got these dumb access points, and then you've got a wireless switch. That's how the wireless is laid out here. That's how wireless is laid out pretty much in every part of the world, everywhere. Right? So what the idea here would be that you would attach an MDC or a cloudlet right next to a switch. And once you do that, all the packets that are going in hit this guy, and then you can decide whether it wants to go to the cloud or not, and you can do this one thing. So that's one way to deploy it, and you can go hit every enterprise, every hotspot, pretty much every hotel, everywhere you want to be. Okay? The same thing, if you think about cellular networks, you can do the same thing. Cellular networks are evolving towards what is called small cells now, and small cells is basically to deal with capacity. You do the same thing. You've got a small cell showing up, and you put an MDC there or a cloudlet there, and it'll do the same. It'll do the needful. Now, it's not, the concept of cloudlets was initiated by us, but we see now that a lot of the technical leaders in the different parts of the world are also starting to talk about it. So I just briefly checked, and I found that, here are some quotes about people pretty much saying the same thing here. So as you can see, in this thing, you've got these devices, and you've got a little device here sitting on the edge. This is from somebody in Intel. And this is from Hawaii. They're also talking about, they actually use the word cloudlet here. They've got base stations, and then you've got everybody talking to a base station and a cloudlet, which talks to a cloud. This is from, I think, Nokia Siemens. They really they show a whole stack here, that software stack that is sitting right here on the edge as well. So this idea, this concept is actually, has got lots of legs here. And there's plenty of literature, both from Microsoft Research as well as other researchers, which show that this leads to a tremendous amount of improvements. Okay, so I'll leave you with this thought, that I think in my worldview, we have focused very heavily on these large mega data centers, right? And what I'm sort of talking about now is to create these thousands of these micro data centers at the edges. Now, for a company like Microsoft, we have to now think about this as a full resource. So just as we look at optimizing the heck out of these guys, we have to now optimize everything. So even if you have put 40 servers per rack here, and you've got 1,000 here, you've got 40,000 servers that you have to optimize. So now you think about things like IoT or Internet of Things. Internet of Things really is about getting all the data, aggregating it, analyzing it, doing something with it. Are you going to bring all your data here, or are you going to just keep it here and analyze and send it back here? So now you think about distributed analytics. You think about Hadoop, MapReduce, those sort of things, and say, how do I think of this entire infrastructure? Because now the network is in the middle, and I have to take that into account when I do job placement and scheduling. So as like I said, as you think about the cloud, you think about the disaggregated cloud, you start to see that a lot of the problems that we have faced in the past are coming back. So that's a short talk.
fantastic, Victor, and it's good to see the work we're doing to try and save on battery life as well as improve performance. So let's hope we get there. So questions from the audience, please.
Yeah. So one advantage of big data center is you can have a few staff members maintaining very large number of machines. Once you go to these mini data centers, then they are distributed. You have maybe a few dozen machines in one place, a few dozen machines in another place. That advantage disappears. Right?
So I thought where you were going with this was you were saying that it's a huge management headache for a company like Microsoft to be able to manage. Because even for us, and I think part what you're asking is, you've got these scales and you can have this cost benefits, but if you've got this disaggregated system, then... So I tell everybody here internally that the world sells the cloud, we too sell the cloud as computes and storage, right? What I want to see is us selling the cloud as compute, storage, and latency. I want to be able to give you guarantees that we can not only give you the compute, but we can perform faster. So now, from that perspective, I think the cost gets amortized as you start to build this out. And as you build the technologies out in a disaggregate, it should be okay. It should not be because it's still a thing.
I was wondering how you see this playing in, if at all, to like developing countries and providing services there, where energy is a bigger issue as well as network speeds.
I think for developing countries, it's actually a great solution. Because when we think about developing countries, we actually think about things like electricity not being there or connectivity. But if you have these micro DCs, you can actually start by building out these micro DCs infrastructures, right? They're smaller. They can be even one rack or two racks maybe. You have a little from power. You can actually deal with that. So this is a good build-up strategy. And when you find that the DCs or micro DCs are not capable of doing it, you start to invest more. So to me, this is actually the right way to go in some of the developing countries, because you can reach out to a lot of people with this sort of stuff very fast.
What types of locations would you put them in? Should they go in like an office building or just a room somewhere, or? Right.
So this is a slightly longer answer, but the two examples I gave you, I picked easier examples because that was a case where you have an enterprise and you already have power and you already have this thing. But I think what we have to do, to be in all honesty, is we have to figure out what reason a man-power ISP will deploy this. So the traditional reason that people do is that they say that we can save you the upstream bandwidth cost by caching a lot of data. So once we are able to add that value, then we suspect that all these ISPs that exist out there, they will find the rack space and power for it. So the onus is it is on us to sort of figure out what that value proposition is for these individuals.
Okay, I think we'll move on. So thank you, Victor. And
thank you.
It's a real pleasure to introduce Albert Greenberg, who was a researcher here in MSR, but's moved across into the Azure team. Victor talked about what happens at the edge, and Albert's going to talk about really what's happening inside our data centers. So over to you, Albert.
Great, thanks. So actually, I'm going to talk about the work of about 160 engineers who are in the networking team distributed between Redmond and Dublin and Silicon Valley, and what we've done over the last 3 years or so. In summary, we filled up the network in the houses that David built, and these are houses of glass and copper, lots and lots of glass for our networks. But we've changed everything. I mean, there's nothing that was really not a plug or a wire or anything that hasn't been rethought, and that's one of the messages of the cloud. Is just the scope for innovation is so enormous, and like you could see in Victor's remarks, what seems like just percent. One of the memes you get from some computer science talks is if it's not 10x, it's not worth doing. But in the cloud, it's not so, right? Because you just get this incredible multiplier from 5%. If you can save 5% or 25% or whatever in the power, it's amazing. So that doesn't mean we're not aiming for 10x, but the small gains have terrific impact. So I want to give you a little bit of Azure by the numbers, just so you get a feeling for how we grew and what scale means. Somehow physically, you have to just get a sense of what is scale here. And then I want to talk a little bit about what these numbers mean for network. And there's a company's been purchased for $1 billion and this and that. So you probably heard of software-defined networks. I want to tell you kind of what that's about, what it really means besides it's cool, and software-defined storage. So this is a bit of a dated picture of the footprint of Windows Azure's mega data centers. Let's see, 25 data centers, and here I'm not showing the edge that Victor talked about. 1 billion customers, 20 million businesses, and 75 markets. It's, again, I guess, just get a feel for what is scale. Maybe 100 developers sounds like a lot of people, but if you look at this kind of growth, it's amazing. You cannot assign a developer to a cluster or a data center or whatever. There's just we're building like crazy. So in 2010 we had 100,000 compute instances, VMs, and now we have millions. As David said, we also have millions of hosts. In terms of storage, we went from tens of petabytes to exabytes over those years. And in network capacity, we went from kind of a skinny traditional network of tens of terabits per second to the petabit per second networks that we build now in the data center. So what does it mean if you want to, if you're an eScience guy or you want to connect to Azure and run your workloads on us, or you're actually big data guy, or whatever it is, what does it mean for you? So really what cloud providers like Azure provide is the ability to create in our environment from a networking guy's point of view, it's whatever virtual network services you want. So we allow you to first of all, with high speed, I won't be able to talk about this, extend your private network into Azure in a convenient way. Click, boom, and you're into Azure. And as well as you don't have to rewrite your network architecture. You can, in particular, use the same IP address space, the same kind of network planning tools and management systems that you're already using, and just extend it into Azure. So one way to say it to enterprises is that when they go to build a branch office or a hub office, they can just extend it in to the cloud. If you don't need that, then you can just, from the beginning, build into the cloud. But you get a virtual network, and in essence, because of the way we do compute, storage, and networking, you get a virtual data center inside a cloud. Okay. And then again, this picture shows that we've got an orange enterprise and a red enterprise, and they're completely isolated, even though they're built on shared infrastructure, and they'll feel like they're dedicated to each customer. The orange customer won't feel the presence of the red customer. So the challenge to all of us that are building in the cloud is just how do you keep up with these numbers? How do you support, for example, 50,000 virtual networks in a single 100,000 server deployment in a data center? Really, the answer is, honestly, software. Which usually starts with finding the right abstractions and the right separation of concerns. One of the sort of natural things for people to talk about is the hardware and kind of the lay of the land. I talked about it myself in the last minutes, but the the software is actually the only way you can get to this kind of scale. And what's interesting is also the impact it's had on the industry. The industry has put a lot of focus on network hardware like switches and routers and things like that, or optical networking things. And they certainly have a major role to play. I could show you some data on how we use them. But the key to this software-defined networking stuff that you hear about and what everybody is using, all the cloud providers are using, is on the host, on the server. Okay, so it's not really honestly about just disaggregating a router. It's about new innovation on the host and host networking. And that's the way you get to deal with these huge numbers that I'm talking about in terms of data centers and virtual networks. And beyond just the numbers, by moving networking down to the host, the networking policy down to the host, and you get the flexibility you need to roll out new features and to debug things. There's no way we could have changed everything in networking if we had to wait for new ASICs to get revved. It has to happen in software on the host, and that's where it does happen. So if you don't remember anything but this one line to remember is in the data center, the action is on the host. So in terms of networking, what does it mean that you think about it, every host performs all packet actions on its own VMs. So that means you've got this massively distributed compute engine that works a lot better than if you try to build some kind of scale-up device that does it in the middle. Victor mentioned our software load balancer. We run software load balancer on every single device and every single host in the data center. So it's really this incredible scale out. So it's a massively distributed system that's put together through host networking. And really the reason it makes sense is that by distributing it this way, a teeny bit of power on each of a million servers comes together to deal with billions of flows. And if you just do the math, then each host only has to deal with 1,000 flows. So you're at the right place where you can apply per flow policy. So the essence is, well, how do you control that? How do you build the software to deal with all those distributed hosts and push this software-defined networking to the host? There's really a lot to say here, and I just grabbed one slide, but there's a lot of talk about in the industry OpenFlow. You've probably heard of OpenFlow, and wondering kind of is it technically mature? Is it really a big deal? Is it just kind of a hype thing? What is it? So the essence of it really is pretty much that you can get stuff done through flow tables that are fairly simple, that provide fairly simple transformation on packets. They move through pipelines. And this happens in a switch that runs on the host. It's called a vSwitch or a virtual machine switch. And by the way, it's not necessarily a layer 2 switch. It's doing a lot of routing. But the main thing is these tables can perform this transformation of packets moving through tables, can perform all the networking functionality you need to perform to get stuff done in networks. And I won't say this is OpenFlow. It's it's similar to the idea of OpenFlow, and a lot of work has been done at Microsoft to make this kind of idea go really fast and scale to huge numbers. So this is kind of the data path mechanism. That's all I have time to show you in this little bit. But there's this thing called the controller up there. That's actually coordinating policy and programming all these switches. All these, there's 100,000 switches in a data center. So that thing is not really one thing. It's a distributed system. It's highly available, highly resilient. And this combination of the virtual machine switch and the controller is what lets you do software control and rapid innovation in the data center network. Okay, so I thought since a lot of you guys are interested in storage and big data, I'd tell you a little bit about storage. So just like we have to virtualize compute and virtualize network, we have to virtualize storage. So there is a software-defined storage industry moving in the data center. As it turns out, storage puts a lot of pressure on the network. Sometimes we use the word east-west, to talk about flows that go from server to server in the network. And if you think about one write in Azure, and there's some interesting papers on this that you can find. It generates a lot of traffic all around the cluster. And the reason is we want to provide amazing durability. We want to, every byte written has to be quickly accessible from the compute cluster and has to be incredibly durable, and so that you won't lose data in the cloud. So we copy it. We copy it efficiently using erasure coding, so this generates a ton of IOs in the cluster. And by the way, it goes over the wide area network to other clusters because we want this data to be available even if this cluster is unavailable because of a fiber cut or what have you. So when you go and do the math of how you build this thing, it's one of the fun things about being in the cloud. You can play with any parameter. You can put more disk, more SSD, bigger NIC, a bigger switch, and so forth. But it turns out, at the end of the day, to make storage cheaper, you wind up spending more on network, and not in a reckless way, but in an engineered way. You build a bigger network to deal with the storage. One of the interesting things is the resurgence in clouds of RDMA, which really a few years ago we didn't think that much about. But really the great thing about RDMA technologies is you get incredible offloads from the CPU. So I think you guys that if you're coming from eScience and you've used InfiniBand, you're used to this. That now your CPU is basically all your networking is offloaded to the hardware, and you've got your CPU back to do your computation. And this is amazing, and I'll show you some numbers about this. So what we're able to do is in the cloud embrace RDMA. We use a technology called Routable RoCE, which is an Ethernet technology that employs InfiniBand transport over Ethernet, and we've got it to route. And this is we're working with lots of industry partners on this. So this allows us to basically take stress off the servers. These servers are expensive. Build a slightly bigger network with the right kind of host support for offloading, again, host networking, and get a more economical result that meets the needs of the storage community. So the bottom line is all the logic is in the host, and now we have software-defined storage that scales with software-defined network. So does it work? So there's just a little screenshot that I have that shows that we're getting line rate with no CPU, zero CPU using RDMA. I didn't want to just say nothing about physical networks. We want these physical networks to be so redundant and so high quality that it's okay if there's an edge that's broken here and there, and there's packets are dropping here and there. We've got lots of capacity. So the problem becomes, how do we just disable the broken piece and not have a panic or a judgment call? Hey, should we fix this piece, or should we keep it available? Do we have enough remaining capacity? We have enough capacity so that if we can keep the software and the monitoring and the automation and all that stuff working really, really well, then we have a lot of capacity in the physical network, like in this little cost diagram shows. so that it's okay for things to break. The bullet points here have to do with, I guess that I have there should be 40 at the bottom. We can get network policy done, like access control lists, network address translation, virtual private networks, software load balancing, firewalls, all that stuff, virtual appliances, network function virtualization, done in the host, and then have this big resilient internal network that can do things like RDMA, for example, that it just needs to be very fast converging and powerful. All the policy pieces, the software, the stuff you want to sort of add new features within is in software, and we implement everything as a VM. And we deploy network services just like any other service. So let's see. Just wrap it up at this point. This term of SDN, I hope I helped clarify it a little bit. I showed you where we applied policy to make it happen. The other thing that it's worth mentioning is that we are, bringing the same technology to a customer premise with our partners in the OSG team. Okay.
Thank you, Albert. I think that was a really fantastic insight into what happens inside the data centers. I certainly found out a lot that I didn't know about. I'm sure there's a few questions. Dennis, do you want to kick off?
That was really fantastic. I get asked by people I work with in the Internet 2 community, and they are totally committed to SDN throughout the system. They keep saying, when will we be able to actually develop couple our SDN clients in the university community directly into Azure? Is that something that is foreseeable? I mean, they're usually open for pretty much.
Right.
But that may not be compatible with what we're doing.
So, really, we offer. There's layers to that question. So, if you want to build your own, let's say, wide area network, Internet 2, then yeah, you can use these kind of ideas to build your own Internet 2, and we do have an effort to do software-controlled wide area networks. Okay, that's maybe one of the things that they want to do. If they instead the idea is you want to bring your own hypervisor or something to do the kind of host SDN stuff that I've talked about. The cloud providers don't provide that kind of bare metal where you can bring your own hypervisor. You basically bring your own image. If you want to bring, let's say you like a certain load balancer or something like that, we want to support that as a service. So you can bring network functions, but you don't. We don't open up so that you can run on the bare metal in our cloud, and no one I think does. To some degree, maybe the hosters do. That if you just buy space and then you can put anything you want in the cage. But we are, I think, fairly open about we publish what we're doing, so there's that kind of flow of information. But in essence, we're telling people that you don't have to do that. If you want to set up shop in the cloud and you want to do big data, you're good. And that's just bring the data to us, and we'll do the heavy lifting for you.
Great. Are there any more questions? Yeah.
Maybe this is just more of a clarification. So you mentioned RDMA and Rocky and all that, which I understand that was between the server and your storage. Will you be able to get clusters with high-speed networking?
Yeah, so this is the question was, did we do that for storage? And we did. Yeah, it's one of the things that we're looking at is going broader with RDMA than we've done up till now, in cluster size and also in field of use.
Yeah, I think just clarifying that as well on Azure, that we've now got the A8, A9 instances for true HPC with InfiniBand running Windows HPC. And we've seen some benchmarks that show actually from one of the universities in Switzerland, that's running faster than our local HPC cluster. So I think we're starting to experiment with that, and we do have a service, but rolling that out more broadly, I think, is something that product teams are looking at.
Yeah, but actually, I was under the impression that we didn't have access to that through our university research as allocations.
Yeah, the Azure Awards are for particular types of instances, but I think if you want to play around with the Windows HPC, talk to us, Dennis. We're interested to see what people are looking for. But as I said, I've just last week seen some benchmarks from a university in Switzerland, and they're looking to just use Azure HPC rather than their own local HPC for a lot of their workloads. So it's, yeah. Are there any more questions? Okay, well, thank you, Albert. That's fantastic. Jonathan Goldstein, who's one of our researchers here, who did go off into product land but came back, is going to talk about sort of eScience. He's one of our experts in big data. We had a session yesterday around streaming data, and I think that's something dear to Jonathan's heart. He's one of the people who sort of came up with the ideas around Stream Insights, which is one of our products. I'll just switch the PowerPoint. It's that one, isn't it? There we go.
Does this work?
Yeah, I think so.
Okay.
So, so thanks, Jonathan.
Hello, everybody. So today I'm going to. So the title of the session was the leading edge of the cloud, right? So I thought it would be worthwhile talking about how this relates particularly to eScience, how we got to where we are, why the gaps are that are there, and what the gaps are that are likely to close, and what are ones that maybe we don't have good answers for yet. So first of all, where is the leading edge, right? So the cloud was originally built basically to serve web pages and to solve the search and the online advertising problem, right? So basically, the cloud, sort of Cloud v1, was basically designed to solve these two problems. So what does that mean? Well, it means that the cloud was built for serving, the cloud was built to handle human-generated request response kinds of workloads where there was some kind of state being stored in the cloud. So you had essentially, think of it as billions of devices, which are people, very slowly entering data into the cloud, which would then be accumulated somehow into some kind of state and possibly served back, right? The other aspect of it is that part of solving the problems related to online advertising and search involved being able to solve very large data processing problems that required massive scale out. Now, the thing that motivated all of this activity was that we knew in advance that solving this problem would be worth more than $10 billion, right? So having very expensive infrastructure as a critical thing to solve this problem was okay. It wasn't a problem. The other aspect is this sort of ubiquitously connected queryability and result dissemination. It's connected to the internet, right? So everybody can get web pages, everybody can search, everybody can do all of those things. The other thing is that there was some sense of sort of pay-as-you-go infrastructure. The more people that connected and used your website, the more expensive it was going to be to do, but the assumption was that you were going to make that money back. And you wanted that sort of scalability as people used it, the ramping up to be transparent and easy. So the question is, does this sound like you, right? As eScientists, right? Does this sound like you? So let's take apart each of these things separately. The first thing, let's talk about the human-generated request response, right? So eScience things tend to have more massive data rates from a smaller number of sensors, right? So that doesn't really sound like you guys, right? Another thing that's worth saying is that it's true that I think the massive scale out aspect of things is in common because you have very large data sets that you want to process. But the thing is, there's an unknown payoff.
I think it's pretty well known. It's zero.
Well, the hope is that eventually it will pay off in some way, which is why NSF funds it, and it'll help society eventually, right? But the point is, you don't know at the beginning. Maybe it's going to be big, right? Maybe the payoff's going to be gigantic. Maybe it'll be nothing. Maybe it'll turn out you don't find anything. You just don't know, right? The other thing is this sort of combination of ubiquitous connectivity and the pay-as-you-go part. And if you ask me, I think the reason you folks are really interested in the cloud is because of all the yellow stuff. It's because it's connected to everywhere, so everybody can share data sets, can run queries against them, can share results, can reproduce them. All of that, along with the fact that, oh wow, there's this opportunity to get a hold of a supercomputer that we can all share to basically do computation. I think these are the main reasons. But those other things, there are these differences, right? So let's dig in a little bit deeper. So let's talk about the human versus machine-generated aspect of things. There's a vast increase in the data rates per source for e-scientists, right? It's not somebody clicking on a web page, it's some sensor that's constantly reporting a result, maybe even video, right? There's a significant but smaller decrease in the total number of sources. You probably don't have 5 billion of these things, one for every person on the planet. You probably have, anywhere between tens to hundreds of thousands of these things, would be my guess. The other thing is, it's worth saying though that the decrease in the number of sources doesn't compensate for the data throughput. So frequently you end up with vast differences in the data scale. You look at something like the amount of data that the Hadron Collider, and there is no business I'm aware of that produces data anywhere near those kinds of quantities. The other thing is that none of the data sources are part of the data center. This turns out to be pretty important because you have to get your data into the data center somehow in order to operate on it. Usually these are sensors that are somewhere in the world collecting data about something. The aggregate amount of data that they all produce is pretty large. If you look at the online advertising case, yeah, it's true that like clicks and things like that and search terms came from the outside, but there's also a lot of data that was collected inside the data center itself that was then logged. So a lot of the data in that case was actually born inside the data center in the first place. In this case, actually none of it is, right? So, all of this adds up to a big data ingress problem for scientific data, right? Now the good news is that there is a solution to this problem, right? And Jim Gray suggested it, to my knowledge, the first I heard of it many years ago, which is you collect the data on some kind of medium, could be a hard drive, could be whatever the future holds, right? And then the idea is once you collect the data and you store it there, you ship it directly to the data center and just physically attach it, right? And the assumption is that you collect it on a medium that's amenable to later data processing. That's pretty important. So that, because copying this data, this is large amounts of data, copying it, moving it over a network, this just is not a sensible thing to do.
There's maybe another alternative in China. The Beijing Genomics Institute built a data center around the sequencers.
So I was gonna hold that. Yes, you're right. There is actually, and this actually plays in a little bit to what Victor was saying, possibly too, right? Which is that one possibility is to bring the data to the data center. Another possibility is to bring the data center to the data, right? So you can kind of go in either direction. Bringing the data center to the data has its own set of problems, but neither of these are super straightforward. So.
Or Microsoft could build a telescope and put it in the data center.
Yeah, exactly. So let's go into this a little bit more, right? About this whole the nature of the sort of the lucrative aspect of online advertising compared to this kind of exploratory, aspect of data science. Well, so I just have, 4 quadrants here. The top 2 are the high investment quadrants. The bottom 2 are the low investment quadrants. And then we have the left quadrants, which are the low return, and the right is the high return. The current cloud computing infrastructure, which was built to solve search and online advertising, is clearly in the high investment, high return category. right? The problem with eScience is that, well, we don't really know. It depends on the activity, and you don't know in advance exactly where you are. Now, to make matters worse, the very high return that we got for online advertising, it was so high, it was such a valuable problem to solve that it allowed us to be incredibly wasteful with the resources, the computing resources that we used to solve the problem. And time to market ended up being a lot more important than whether or not you were efficiently using the resources that you had. In order to sort of get a grip on all of that, so Hadoop can process about 1 to 10 megabytes per node per second, right? That's about what Hadoop can do. Now, everybody's excited about Spark because Spark's a lot better, right? So Spark can do maybe 5 to 50 megabytes per node per second. That's a lot better. That's a 5 times increase in throughput, right? We must be doing great, right? Spark must be great, right? Well, maybe not. By comparison, main memory databases can process very similar queries at rates of about 1 to 10 gigabytes per second per node. So we're talking about a difference in levels of efficiency between 100 and 1,000 factor. It's huge. So it takes 1,000 Hadoop nodes to do what one of these can do in a single node, right? So that's a level of inefficiency that's pretty staggering. Now, if you need 100,000 machines to solve your online advertising problem, and your online advertising problem is worth $10 billion, you shrug your shoulders and say, oh, well, I'll just go ahead and do it anyway because I know how to scale that up to 100,000 nodes. I don't know how to scale up that technology to 100 nodes. So I'll just pay the price and oh well, right? But does this sound like a recipe for success for an exploratory data processing task where you don't know in advance what the return is going to be? Does it make sense even to spend that money, right? And now it is worth saying that these databases that I'm talking about have limitations, right? They only allow you to express certain kinds of queries. And I think that actually a very rich area of work, which actually is the area I'm working on right now, is basically saying, you know, how can you reduce this efficiency gap while at the same time not limiting yourself to the expressiveness that these database engines have, and significantly expanding the scope of the kinds of computations that they can do enough so that they're useful to eScientists, right? There's a lot of ground to make up here, right? Now, unfortunately, the bad news is that we may ultimately be limited by networking, right? It's worth saying that today's technology for these in-memory DBs is 1 to 10 GBs per second, but with the new Sandy Bridge architectures that are going on and all the improvements in microprocessor and computer design, we have every reason to believe that in the pretty near future, the 1 to 10 is going to turn into 10 to 100. So, 10 to 100 gigabytes per second, we all feel like we'd be doing really well if we maxed out our 10 gigabit NIC, inside the data center. So there may be a 1 to 2 order of magnitude difference between the throughputs that you can get sending data from machine to machine versus the kind of bandwidth that you can get between main memory and your microprocessor. So it may be that that networks will fundamentally limit us here. Now, the good news is that the ubiquitous, sort of connectivity and the pay-as-you-go aspect of it, well, that's kind of motherhood and apple pie for everybody. So I think actually our current data centers do a pretty good job there. Now, there's one other axis of difference. I was just talking to Ed Lassiter before this, and there's one other axis of difference that he pointed out that I think is worth mentioning, which is data longevity, right? Which is to say, in the online advertising problem, once data was a year old, no one cared about it anymore. It really had no relevance anymore for either search or for the behavior of people, for ads, and all these kinds of things. So really, data just kind of got thrown away, after a year or so. Ed pointed out that a lot of scientists want to keep their data for something like 50 years. And as time goes on, there's maybe reason to believe that it'll just sort of continue to be valuable over those 50 years. So that's also an important part of that. Now, my suspicion, I was thinking about that, and my suspicion is that problem probably will get solved just because companies are incredibly paranoid about losing data. So they may, in fact, in this whole service thing, force us to cope with that problem anyway, just because of their own internal paranoia. So there may be significant market pressures for us to address that problem. So that is my talk, and if anybody has any questions. In part, this was designed to spark a conversation. So feel free to jump in, and I want to hear opinions and comments.
Okay. Thank you, Jonathan. Slightly controversial things in there, I think. So, has anyone got any comments? Does anybody agree or disagree with Jonathan? Tanya.
I mean, I very much agree with the point that for a lot of scientific data, we cannot build a data center where the data are coming from. We actually have to the big problem is getting the data to the cloud. And with that comes also a trade-off not only of sort of how do you use the cloud, but do you use it infrastructure as a service? How much of it do you do locally still with whatever biggest computer you can get versus on the cloud? And this trade-offs, I don't think we've explored yet enough of what's worthwhile and when you actually have to pay the cost of getting data to the cloud.
Yeah, it does kind of feel like there's sort of a big discontinuity between, I can run my data on my machine in whatever my version is of my local in-memory DB that I can get really good performance on. Once the data kind of reaches a certain size where it starts getting really difficult, or nonsensical to do that. At some point, you have to sort of bite this bullet and pay this price and say, oh, well, I'm going to flip a switch now and put this data up in the cloud. That's a hard switch to flip. I think that's kind of your point. Is that it doesn't feel like there's any sort of continuum. There's sort of this hard switch that you have to flip.
Right. It's also not like it. At least I don't well understand yet the trade-offs of sort of the expense of getting the data there, the computational, the infrastructure is a service, the computation is a service, and so on. All these trade-offs are not clear of what should we put on the cloud. Clearly, if we want to share data, we should put some part of those data on the cloud. Clearly, if your data are big, you should put you should put your data on the cloud. But at what point should we add computation, to go with it versus do some of it locally? What are the trade-offs?
I wonder a little bit whether what Victor talked about, whether his sort of microclouds could sort of help with things like that, because maybe that can give you more of a continuum, and maybe if it's even something that can be on premise, you can become part of the cloud or something like that. I don't know. It's like kind of spark some thoughts for me around maybe the cloud doesn't have to be this totally monolithic thing where you send your data there and it's this big thing you have to do. Maybe you can bring it to your data in pieces as you need to, or something like that.
Jeffrey.
Mm-hmm. Listen to one of the other talks. Why can't we use SDN and RDMA to link our data in our local data directly to Azure?
I think that's what Albert was showing, and it's actually something we've been doing with Janet in the UK, where we've got now a dedicated 10 gigabit per second direct connection into our Dublin data center from Janet. So all of the UK universities now, and this is I think it just went live. We haven't made a big public announcement. We've been working with Janet for about the last 18 months on this, where we have a dedicated private network line between the UK academic network and our Dublin Azure data center at 10 gigabits per second. And so, again, we are trying to work with the research community to look at this, and very much with the Azure for Research program, as we've now getting towards 150, 200 projects. It's interesting, the hybrid approach of local plus public is certainly something that we're seeing. And I think as Microsoft, as an organization, that is our strategy as a company, really, is hybrid. And so, yeah.
Why can't we just ask Internet 2? I don't want a dedicated line. Why can't I ask Internet 2 to take my either my local computing or my local storage and connect it in this seamless fashion to Azure using host SDN and
well, I was at the.
What's wrong with that?
So next month is Terrana, which is the International National Research Network Conference, and last year at Terrana they did, all of the talk was about SDN, all of the national research networks, not just Internet 2, but the other ones, and not just other US network providers, not like in California. So I think SDN actually is something that all of the national research networks are moving towards, and we are working with them. Surfnet in the Netherlands, where we have an Amsterdam data center, for instance. So I think, as well, just from the research community, if we know that that's what you need, then that helps us to talk to the national research networks. Jeff.
So are we fooling ourselves a little bit by focusing on these immense data sets? Like the National Ignition Facility generates a terabyte, in some number of nanoseconds. Okay, well, obviously the networks can't handle that. But a big data set, at least in my terms, are the satellite data, satellite images. Well, we get the data down from the satellite, right? And so,
that's a really thin
if we can get the data down from the satellite, it shouldn't be a problem to get those data onto a disk somewhere, right?
So the question is, what kind of throughput are we talking about?
We're talking about, sort of 100 megabits per second, sort of.
100 megabit per second, so like 10 megabytes per second or something like that.
Yeah,
yeah that seems to me like that's something you could do.
The thing is that it's, it does go on 24/7, right? But on the other hand, we have communication satellites. The data come down.
But you know what I think frequently happens?
In fact, people that are really interested in low latency build their own receiving stations.
So there's sort of two comments. The first is that I think part of the problem that people face when they have things like that is that everybody knows satellites are expensive, and everybody knows that launching satellites are expensive. So when they kind of budget these things, they say, oh, okay, well, I have this much money to sort of launch my satellite and develop my satellite and all of that. They don't necessarily budget in all of the things that people are going to want to do with the data once they have it, right? So the question is, if you want to keep this data for 50 years and you want to allow somebody to run queries against it, part of it is this collection thing, this continuous collection thing. But then even after you've collected it, somebody has to continuously pay to curate it and keep it available for everybody so that they can essentially answer questions with it. And that's an ongoing cost that never really ends, and it needs to be, the question is who pays for it? Does the person who puts the satellite up there pay for it? Does the person who runs the computation task pay for it? Because if it's the person who runs the computation task, for instance, then okay, now who pays for data curation? So there has to be some kind of business story around, it's worth it for me to curate this data because I'm confident that people are going to come to it and ask questions which I can then charge them to produce answers for or something like that.
Well, but I guess there's, so first of all, there is an archive that is paid for by the taxpayer.
Mm-hmm. So that archive, so my point is if that archive is a bunch of offline tapes, for instance, then it's not really very useful in that form. If I'm going to run a query against it, now suppose I want to get that data and run a query against it, and it's pretty large. It may only be 10 megabytes per second, but now accumulate that over 10 years, right?
Well,
that's actually like a fairly significant amount of data.
Well, I guess though one of the issues though is it's somewhat like a model computation in that it is recoverable, all right? Mm-hmm. And so years ago during the Sequoia 2000 project, Joe Pasquale kind of looked at this issue of, there's a cost to store, there's a cost to compute. In this case, there's a cost to retrieving it from another archive. And based on usage and some cost trade-offs, you can kind of decide when you can when you can throw data away. Mm-hmm. Because if in principle it's recoverable.
Right, and in the end, I think it all goes back to that. It all goes back to economics in the end, right? I mean, you hold on to the data if you hold on to the data in queryable form if you think it's going to be valuable enough to make it worth your while to hold on to it, and then disseminate it for tasks where you think that the expected return warrants the cost that you're going to pay. you know, or something like that, right? And it is fuzzy because it's science and we don't always know, we don't know what the outcome is going to be in advance, right? But these are like very critical problems we have to solve, you know, as part of solving this larger problem. We have to really think through this stuff very carefully about, you know, who curates the data and why, and make sure they're motivated. In what form is the data? Is it very cold? Is it warmer? Do I have it spinning in disks somewhere? I'm ready to query, you know, just in case somebody. I mean, somebody needs to decide all these things, and you can't divorce it from the economics. I guess that's partly what I'm saying. Yeah, yeah.
I think that's one of the things that, like, the Research Data Alliance is trying to grapple with that globally, right, across all the disciplines, and a lot of these questions are common across geosciences, all of them. So I think
absolutely, and sort of version 1 of the internet, you know, of these clouds, actually the economics weren't aligned, I think, with what scientists would like, and I think that's changing. I think there's enough motivation to go after problems that aren't just $10 billion problems, that efficiency is mattering now. I mean, you saw the number of customers we want to support, we are supporting in Azure, and I guarantee you there's 10 times more than that we want to support. And we won't be able to lure them, you know, onto our cloud without addressing these efficiency problems. But the original problem that motivated our cloud design was one that had such a high level of return that it allowed us to not worry about efficiency to a pretty large degree.
I think we're just going to, I think there's a lot of interesting discussion here that would be good to continue over lunch. So I don't know, Jeffrey, did you have a quick one, or is this a lunch discussion? or in the bar afterwards?
I was at some meeting about scientific network, and I asked the people there that, as far as I can see, scientific data was an absolutely negligible fraction of the total amount of data. And so why on earth do we need special resources? Because we're within some fluctuations. Therefore, it ought to be possible not to have special programs and just solve it on top of the commercial infrastructure. And they did not like my question, nor did they actually answer my question.
But actually I saw the numbers that it's exactly the other way around, that there's more scientific data, sheerly numbers that today that's produced by
So I think this is live though, right? What we do, when we want to make scientific data look really big, we cite about 3 or 4 projects. And when we want to make it look small, we cite the other 99.9% of the projects in aggregate.
But the total amount of data is meant to be 4 zettabytes, and the LHC is tens or hundreds of petabytes. Is a negligible fraction.
But I think
even stronger. But I think even if you grant that maybe there's some of these projects are producing a lot, if you ignore those 3 or 4 projects that are going to do their own thing anyway, I'd like to figure. I sort of agree that we need to. The rest of the project can be handled in the noise, perhaps.
But Dennis, do you want to wrap up?
I just was going to say Facebook delivers more photographic images to people in a day than LHC is generating in its entire lifetime.
But
there is far more non-scientific data than there is data.
But the total amount of data is a lot less important than the variety of tasks and the value of those tasks that people want to do with the data, right?
That doesn't affect the network. The network is the network. It doesn't care about variety.
Depends on how much you move it.
It does.
I think this is definitely sounds like a lunchtime discussion. So thank you all the speakers in the panel, and we'll reconvene at 12:30.